Pascal's Pentachoron, an expansion of Pascal's triangle into 4 dimensions. What is this, you may ask? It's an extension of Pascal's triangle into 4 dimensions, as I just said. Each layer is a 3-dimensional tetrahedron. Each tetrahedron contains 2-dimensional triangular layers. What is a pentachoron? A pentachoron is a 4-dimensional polytope. The polychoron is the 4-dimensional equivalent of a polyhedron. The tetrahedron is the result of folding 3 triangles together and having room for just one more to fit. Thus, it has 4 faces. In 4 dimensions, we call faces cells. The pentachoron is made in the same way. 4 tetrahedra are folded together into the 4th dimension, and there's just enough room for one more to fit. Thus, it had 5 cells. Note that this is one more than the number of dimensions. What about 5-dimensional simplices? That would be a hexapontron, made of 5 pentachorons folded into 5D with space for one more. And of course, we can generalize this to higher dimensions. A lot of people seem to believe that time is actually the 4th dimension. I'm going to give some evidence as to what I actually mean by the 4th dimension. Albert Einstein postulated that time is a dimension just as the 3 of space are. Superstring theory says that there are 9 spatial dimensions and 1 temporal dimension, so 10 in total. Of course, superstring theory hasn't been, per se, proven yet. In the axes of space, you can move in both dimensions. For example, you can move left or you can move right. You can't do this in time, since you're always moving forward in time, no matter what you do. You just can't move backward in time unless you travel faster than the speed of light. If you were to count time as a dimension, then the pentachoron would be a 5-dimensional shape. This would also mean triangles are 3-dimensional, and tetrahedra are 4-dimensional. This is why geometry largely ignores time. If time weren't ignored, then if I were to put a triangle on your screen for 2 seconds, with a height and width of 2 inches, technically this would be a triangular prism, and its depth would be 2 seconds. Here we are supporting that there's a 4th spatial dimension, not temporal. Now before we think about 4 dimensions, let's think about 3 dimensions. You guys should know what Pascal's triangle is. So let's first look at Pascal's tetrahedron. This is just an expansion of Pascal's triangle into 3 dimensions, into a tetrahedron shape. It's also known as Pascal's pyramid. Looking closely enables us to see a pattern. If we isolate, say, the 3rd layer, remember the topmost is 0. It's just regular Pascal's triangle, but each row is multiplied by the corresponding number in the same row as the layer you're in Pascal's triangle. This will help us in our generalization later on. Now let's put this into a formula. We can use this to derive a functional formula for getting a value from a coordinate on the tetrahedron. The linear position can be called k, and the linear layers in the triangles can be called ny, and the tetrahedron's triangular layers as nz, or nz depending on where you are. Let us call this function sa3 from the Devanagari letter sa, and the fact that this is in 3 dimensions. Thus, on your screen is the left side of the formula. But the left side of the formula is really the easy part. We now need to get the right side of the formula ready. The formula for a coordinate on Pascal's triangle is on the right. It's already been found out quite a while ago. Recall that, for example, in tetrahedron layer 3, that's on the right, triangle layer 2, the 3, 6, 3, is just 1 to 1, or Pascal's triangle layer 2, multiplied by 3, which is Pascal's triangle layer 3, wherein k equals 2. Let us call the function for Pascal's triangle a. And a is also shown as one of the notations on the right. To get a coordinates value on the tetrahedron, just multiply a, ny, k by a, nz, ny. Now that we have that, adding one more dimension won't be that difficult. Our 3-dimensional formula is on the screen. Similarly, we can determine that the 4-dimensional version of that formula is what's on your screen now. Note that we had added one more term. This enables more higher dimensional generalizations. Now let's get to the fun part, where we generalize this to higher dimensions. Recall the four-dimensional formula. Let's rename k to n0, and every n sub something thereafter to n1, n2, and so on, all the way until n3 in this case. Rewrite the four-dimensional formula as what's on your screen now. Notice that the subscript of the second n in the function, for each one, is one less than the first n. I'm talking about the right side. For each added factor, the subscript of the first n also increases by 1. So also the second n will also increase by 1 for each added factor. Recall the rewritten four-dimensional formula. Now let's replace saw4 with saw_m, wherein m is the dimension. So now we can actually generalize it. Notice that the last subscript of n is m-1, since it's in 4 dimensions and the last n is n sub 3. We can rewrite this entire thing in big pi notations, and then we get the formula for higher dimensions. Note that in the formula that I wrote, I used the other notations for Pascal's triangle coordinates. And finally, we get our final revisions to our formula. If we want this formula to work in 2 dimensions as well, we need to incorporate the original Pascal's triangle formula into it. This generalizes to dimensions lower than 3, which in this case would only be 2, since it would not make sense to have Pascal's line. That's just nonsense. And there we have the final formula, wherein m is the number of dimensions in the simplex, and nr, wherein r is a number between 0 and m-1, is an actual coordinate on Pascal's simplex. To conclude, Pascal's triangle can be expanded into 3 dimensions with Pascal's tetrahedron, and 4 with Pascal's pentachoron. Using patterns seen here, we can generalize Pascal's function into higher dimensions. This enables us to better determine multinomial expansions. Recall that Pascal's triangle allows us to get binomial expansions. Similarly, Pascal's tetrahedron can get us trinomial expansions, and Pascal's pentachoron gets us tetranomial expansions. And finally, after this slide will be a montage of Pascal's pentachoron all the way until layer 7 of it. And yes, I did do it by hand. Don't ask why.